let's learn about Riemann sums. We're in section 6.2, the fundamental theorem of calculus. Last time we learned how to approximate the area under a curve, I should say the net area under a curve, using left endpoint or right endpoint rectangles. Now we're going to learn how to find the precise area under the curve. Now I will just say that we're going to learn it, but I don't really want you to memorize this technique because it's long and complicated, and it's kind of a dead-end technique. We're going to very quickly learn a faster way to do this. So I want you to see how it's done, because it's good for you to see it, but you can feel free to skip over it, watch it at double speed, or whatever. And I'll mark the parts where you don't really need to know this for the test. So anyway, suppose I give you a problem like example 1, right? Find the precise area under the curve. By the way, when I say area under the curve, I mean net area under the curve, right? Pretty basic function, y equals 4x plus 3. We can actually graph this one. It's going to be something like this. Something like that. And it's just a line. It's got a y-intercept of 3. This is not going to be totally to scale, but the curve is something like this. It'd be something maybe a little bit more like this on the interval from 2 to 7. Again, this is not to scale. It would be a lot steeper than this. But just to point out, this is from 2 to 7, to 7, right? And we actually don't need any fancy techniques. We just need basic geometry. The area under this curve, right? This is just a trapezoid. Now, you could even break it up into a triangle and a square if you really wanted. But the fact is, let's see, we just need a couple of points. Well, we know right here that f of 2 is going to equal 4 times 2 plus 3. That's going to give us 11, okay? And I guess it would be good to know f of 7. It's a little bit off the axis, but I think we can still manage. F of 7 is going to equal 4 times 7 plus 3, and that's going to equal 31, okay? So let's see. I mean, I guess it might even be a little easier to do the whole triangle and square trick, right? So again, I can't emphasize this enough, not drawn to scale. This is a length right here of 5. This right here is a length of 11. This right here is also a length of 5, and this right here is a length of 20. Okay, so the area is going to equal 1/2 base times height plus, base times height, or length times width, or whatever you want to say. So anyway, this is 50 plus 55 for a good old-fashioned 105. Okay, and that is the precise area, no approximation. Okay, now that was a pretty straightforward shape, so we were able to get away with it geometrically. But let's look at the rectangle method and see if we can find a precise, exact way to do it. Okay, so if we use infinitely many rectangles, then this technique is called Riemann sums. I guess it was Riemann who came up with this sort of thing. So did Leibniz and Newton. But anyway, typically it's best to use right-hand endpoint. It doesn't really matter, but I use right-hand endpoints. It's how the textbooks usually do it, so that's how I'm going to do it. All right, so what we're going to do is we're going to start off the same way we always do. We write delta x, which is b minus a over n. And I don't exactly know why I wrote a second equal sign. I guess in this case, for our specific case, we do have that it's 7 minus 2 over n, which equals 5 over n, right? All right, so the area equals, now normally I would sum up just like, I don't know, 5 rectangles or whatever, but I guess now we have infinitely many rectangles. So I guess what I should do is I should write it, and this, by the way, I'm just going to point this out here. Don't need to know don't need to know. I'm just going to put this right here. But I want you to see it, but you don't need to know it. So feel free not to copy this down. Okay? Anyway, the area is going to equal a bunch of length times widths, right? Well, remember how we do this. It's going to be f of a plus delta x times delta x, right? Remember, this is the height of our rectangle, and this is the width, right? And we're just going to keep doing that, right? Plus f of a plus 2 delta x times delta x. Again, height times width, right? That's all we're doing. Maybe I'll even use the green. I feel like I usually use the green highlighter to talk about the height. The yellow highlighter to talk about the width. So anyway, we just keep doing this. Plus blah, 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 blah. And remember that because we're using right endpoints, we keep going until we get to f of b, actually. But it's a plus n delta x. Okay, and again, there's your width, there's your height. Okay, and I guess I should point out that we're doing this, like, this is an arbitrary number of times, right? N number of times. But if we really want to find the exact area under the curve, like exact, and we need to use infinitely many, well, I guess we really need to take the limit as n approaches infinity of all this stuff. Now, one quick adjustment. One thing we can note is that if we're multiplying by delta x every single time, I guess we could write this as the limit as x approaches infinity of f of a plus delta x plus, and I'm not going to write the middle terms, I'm just going to write the last term here. F of a plus n delta x. And then on the outside, I'm going to write delta x, right? Because I'm multiplying by it every time, right? There's no need to keep writing times delta x, times delta x. That was useful when we realized, hey, we're just taking a bunch of areas of rectangles. But I'm just going to stick it on the outside, okay? Anyway, let's plug our stuff in. Now, we know what f is. It's 4x plus 3, okay? And we also know that a, just to point out, a equals 2, and delta x equals 5 over n. Okay? So anyway, we're going to have f of 2 plus 5 over n plus blah, 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 plus f of 2 plus n times 5 over n. Note that that's just f of 7 in this case. We'll still leave it. And then all of this is times 5 over n, right? Because that's what delta x equals. Right. Maybe I'll even just keep this green. Okay, well, we actually know what this equals because we know what f of x is, right? So we can just write this as 4 times 2 plus 5 over n plus 3 plus blah, 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 plus 4 times 2 plus n times 5 over n plus 3. And feel free, if you really want to write 4 times 7, you can do it. It's fine. It's not going to help you. It's not going to help you. But whatever. Anyway, we're just going to do a whole bunch of simplification at this point, okay? A whole bunch of simplification. I'm going to distribute the 4 to the 2 to the 5 over n. Same thing over here. Just going to do a bunch of that, okay? So we're going to get, let's see, what are we going to get? 8, that's an 8 plus, I guess I'll write this as 20, or I'll write that as, should I write this 20 over n? Yes, I will. 20 over n, right? I just distributed the 4. Okay, and then it's going to be plus 3, plus blah, 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 and then plus 8, plus 20 over, oh, and actually be a little careful over here. 20 over n times n. You could think of this as 20 over n times 1, 20 over times 2, etc. 20 over n times n plus 3, and this is all times 5 over n. Now, note that we can, because this is absolutely convergent, that's a little technical here, but it turns out we can rearrange our stuff a little bit nicer. We can rearrange this as, note that we have, I'll use blue for this, 8 plus 3, 8 plus 3. We have that n times. So we can go ahead and write this as 11 plus blah, 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 plus 11 n times plus, and then it turns out with a little bit of simplification, we have 20 over n times 1 plus 2 plus blah, 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 plus n. Okay, because 20 over n is being multiplied by 1, then it's being multiplied by 2, then it's being multiplied by 3. That's all the way up through n. Okay, and then all of this is being multiplied by 5 over n. Now let's think about this for a sec. 11 plus 11 plus 11 plus n times is going to equal 11n. Okay, 20 over n, 20 over n times 1 plus 1 over n, okay, plus 1 plus 2 plus 3, etc. Now that's not quite as obvious. This is just an identity that's known. Turns out it's going to be n times n plus 1 over 2. And then all of this is being multiplied by 5 over n. So just to point out, all of this became this. Again, this is not something you need to know, but I just think it's cool to show you. Anyway, if we keep going with this and we simplify a little bit, look what happens. The 11 over n and the 5 over n, if we distribute that 5 over n, we just get 55. I hope this is starting to look familiar because we're going to wind up getting 100, right, with the n's canceling out the way that they do, 100n plus 1 over 2. And then we take, and that's going to be over n, actually, because we do have an extra n from the 5n, right? And so when we take this limit, we're going to wind up getting 55 plus 100 over 2, which is 55 plus 50, which is 105. And we know that's the right answer because we found that geometrically. So it turns out we can use infinitely many rectangles and just, a bunch of arithmetic and also a handy identity and get our answer. Now, the only piece of knowledge that we really didn't know from all that was this. I had to just slip that in there. It is true, you can prove it using induction. But anyway, let's consider example 2. Okay, yeah, so I'll just state it right here. Remember when I said that the area equaled, I said it was 8/3? Okay. Well, now we know that it really equals the limit as n approaches infinity of f of 0 plus, what's that going to be, 2 over n times 2 over n plus blah, 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 plus f of 0 plus n times 2 over n times 2 over n. Right? There you go. So at this point, by the way, I do want you to take notes right here. This will actually help you potentially with homework even. We're going to use sigma notation just to reduce the amount of work we need to do. We write this to mean the sum from I equals 1 to n of I. Right? Now pause the video and see how you can get this. This means the sum from I equals 1 to n. And I is an index term, and it just increases. Right? So when I say this, right, that means I is going to start at 1, and I write a 1. And then we increase I by 1 to 2, and then I is 2. And because there's this sigma here, it means that we're adding all those terms, right? So this term, for example, is going to equal 5 times 1 squared plus 2 plus 5 times 2 squared plus 2 plus 5 times 3 squared plus 2, right? I'll write it all out, plus 5 times 4 squared plus 2 plus 5 times 5 squared plus 2 plus 5 times 6 squared plus 2. And if you wanted to write something in sigma notation, then you would just write it. In this case, you'd write it as the sum from I equals 1 to, I guess there are 5 terms, so we'll put a 5 there. And it would be, I guess it would be 2I minus 1, right? Because 2 times 1 minus 1 is 1. 2 times 2 minus 1 is 3. 2 times 3 minus 1 is 5, etc., etc. So from our previous example, right, remember we solved this guy before? We could have actually written this as the sum from I equals 1 to n of f of, it looks like it's 2 plus I times 5 over n times 5 over n. Because this number is getting indexed. Everything else stays the same. Everything else stays the same. That's the only number that's changing. Okay? So we could have done this problem, instead of writing the plus dot dot dot, we could have written it like this. And it turns out it would have worked out similarly. Anyway, let's solve example 2, and maybe now we'll use a little bit less writing. Okay? And this again, you don't have to know this. But I'd like you to, because, you know, we did mention this before, and now you can see how we get the answer. Anyway, we know delta x equals b minus a over n, which in this case is 2 minus 0 over n, which is 2 over n. So the area is going to equal, actually, I'm just going to copy a little bit here, right? Just copy this guy. That, which using summation notation is going to equal the sum from I equals 1 to n of f of 0 plus I times 2 over n times 2 over n. Okay, and at this point, we're just going to do a whole bunch of arithmetic, make it work out. This is the sum from I equals 1 to n of, so it turns out this is really just, do you see that because it's f of 0 of that, 0 plus that, we can just get rid of the 0 plus, and we have I times 2 over n, right? Just get rid of this guy, right? Anyway, keep it up. We know what f of x is, it's x squared. So it's going to be I times 2 over n, quantity squared, times 2 over n. And we can actually just simplify this. This will be I squared times 4 over n squared times 2 over n. Now, just noting that the sum of the I squared part is the only thing that's tricky. We can actually just not worry about the n stuff. Turns out you can just factor it all out and just take it on the outside. And it turns out, well, number one, we can simplify this to just 8 over n cubed. And it also turns out that we have a nice little identity here, which is going to be, and again, this is just an identity you need to know, it is n times n plus 1 times, oh gosh, I want to say it's like 2n plus 6 or something like that. Oh, no, it's 2n plus, I think it's 2n plus 1 all over 6. That's what it is, all over 6. That's what it is. Again, this is just an identity. You don't need to know this. Again, you don't need to know how to do any of this, but I just want to show it to you. Again, you can look it up, okay? Anyway, you can cancel out one of the ends if you want, or you could just take the limit. Note that the degree on the top is 3, degree on the bottom is 3, and we wind up getting 8/6, or, oh wait, so, sorry, not 8/6, it's actually 16/6 because of this 2 right here. So it winds up being, it's 16/6, or, as promised, 8/3, right? So that's our answer. And that's all for this video.